This week's problem is a counting problem. It centers around a combinatorial method that will allow us to allocate 18 shots to 4 different basketball players. So to be clear, the order doesn't matter here. You can think about it like you were given 18 basketballs, and you're lucky enough to share a gym with Ray Allen, Kobe Bryant, Steph Curry, and Luka Doncic, and the decision you need to make is how many shots each of these 4 superstars are going to take. In this completely unnecessary animation, the greatest shooter of all time, Steph Curry, took 7, Kobe and Luka took 4 each, and Ray Allen took 3. To make things a little mathier, really what we're trying to do is find unique solutions to the equation A plus B plus C plus D equals 18. But here we have to be a little bit careful because the English language isn't as precise as math. The original question asked was how many ways can 4 players take 18 shots? And I'd argue that that's a little bit of an ambiguous question. For one, I don't think it makes clear that order doesn't matter, although that's a caveat that I already mentioned earlier in the video. But that's not the end of the ambiguity. Could a player take 0 shots, for example? I mean, clearly a player is capable of taking 0 shots, but if a player took 0 shots, would you really have 4 players taking those 18 shots? I don't know. I guess you could kind of argue it either way. I think this would be a good point to define our question a little bit more clearly, and maybe even add in a couple extra criteria that will make solving it a little bit more interesting. Let's consider the number of unique solutions to the equation A plus B plus C plus D equals 18, where A, B, C, and D are integers greater than or equal to 2 and less than or equal to, 8. In terms of basketball, how many ways can 4 different players take these 18 shots? But to keep all the superstars happy, let's make sure they all take at least 2 shots and nobody takes more than 8. Okay, so now we've got a well-defined question, but how are we going to solve it? You know what's coming. Consider using the stars and bars method. Ah, nice, stars and bars. That's one of my favorite combinatorial techniques. Yeah, I have favorite combinatorial techniques. Go ahead and judge. The key to understanding stars and bars is understanding how the simulation that we showed earlier, where Steph took 7 shots, Kobe and Luka took 4 shots, and Ray Allen took 3 shots, can be represented by this diagram. The 3 partitions create 4 different groups, and the number of basketballs in each of those different groups represents how many shots each of the 4 basketball players take, respectively. As you'd probably guess, typically instead of basketballs and brick walls, people use stars and bars in these diagrams, hence the name. Anyways, if you see how this diagram represents the solution where A equals 3, B equals 4, C equals 7, and D equals 4, maybe you can convince yourself that any arrangement of the bricks and basketballs will produce a viable solution to the equation A plus B plus C plus D equals 18. Even the weird solutions where a player doesn't take any shots, or some player takes all of the shots, come from some arrangement of the bricks and basketballs. And maybe you're like, wait, I thought that each player had to take at least 2 shots, and no player could take more than 8 shots. Yeah, that's all true, and those are details we'll work out later. For now, I just want you to realize that any arrangement of the bricks and basketballs produces a unique solution to our equation, and any solution to our equation can be represented uniquely by an arrangement of the bricks and the basketballs. So let's figure out how many ways you can arrange 3 bricks and 18 basketballs, because that will tell us how many unique non-negative whole number solutions there are to the equation A plus B plus C plus D equals 18, which admittedly is not the question posed in this video, but it's a step in the right direction. So to figure out how many ways we can arrange the bricks and the basketballs, note that we have 3 bricks and 18 basketballs, so we have 21 objects. I like to picture 21 blanks in which I will be putting these bricks and basketballs. And really, you can focus on just the bricks. For example, suppose I chose the 5th, 10th, and 15th blanks to put the bricks in. Then I'd have no choice but to fill the remaining 18 blanks with the 18 basketballs, yielding this diagram where Ray Allen, Kobe Bryant, and Steph Curry each took 4 shots, and Luka Doncic took the remaining 6. So how many ways can I choose where to put these bricks? Well, if you're familiar with the combinations formula, it's just 21 choose 3. But I like to avoid using formulas wherever possible, so maybe I'll take a more intuitive approach. Let's place the bricks one at a time. When I place the first brick, there's 21 open blanks, so I have 21 choices of where to put it. Regardless of which blank I choose, there'll be 20 blanks left for me to place the second brick and 19 for me to place the third brick. But wait, remember earlier when we chose the 5th, 10th, and 15th spots to put our bricks in? Imagine instead we chose the 10th and 5th and 15th spots. We'd end up choosing the same 3 spots. If we treat the bricks as distinct, we're going to end up double counting lots of different arrangements. In fact, the 21 times 20 times 19 ways that we can arrange bricks 1, 2, and 3 count each unique arrangement 6 times because we can shuffle the 3 bricks in 6 different ways. 3 options for the first brick, 2 for the second, and 1 for the third. To account for this double counting, we divide by 3 times 2 times 1 to get an expression for the number of unique ways we can arrange the 18 basketballs and the 3 bricks. So that's the answer, we're done? No. Remember, these arrangements allow any of the values of A, B, C, or D to be equal to 0, and they don't cap those values at 8. If we want to make sure every basketball player takes at least 2 shots and none take more than 8, we have to account for these 2 restrictions. Let's do them one at a time. First, the restriction that each player must take at least 2 shots. Well, that's easy. Just start by giving 2 basketballs to each of the different players. Instead of thinking about arranging 18 basketballs and 3 bricks, think about just arranging the remaining 10 basketballs with 3 bricks. Well, we'd have 10 plus 3 or 13 blanks, and we just have to remember that everyone's already taken 2 shots. So an arrangement like this would really mean that the players took 2, 5, 8, and 3 shots respectively, adding 2 to the number of basketballs seen in each group. So how many arrangements are there of these 10 basketballs and 3 bricks? Well, 13 choices for where to put the first brick, 12 for the second, and 11 for the third. But again, we'd have the issue where we're overcounting, so we'd have to divide by 3 times 2 times 1. A little simplification, and we see that the number of ways that 4 basketball players can take 18 shots if each one takes at least 2 shots is 286. We're almost to our final answer. We just need to account for our final restriction that no player take more than 8 shots. Well, to take more than 8 shots, a player would have to take at least 9 shots. So let's start by assuming that one of our players took 9 shots. Kobe Bryant was always something of a ball hog, so maybe it makes sense to start out by assuming that Kobe took 9 shots. Remember, we still need everybody to take at least 2, so we'll also give 2 shots to Ray Allen, Steph Curry, and Luka Doncic. That leaves us with just 3 balls and 3 bricks, or 6 objects, to allocate using our stars and bars method. An allocation like this, for example, would mean that Ray Allen took no more than the 2 shots we've already allocated him, Kobe Bryant took 1 more than the 9 we've already given him, Steph Curry took 2 more than the 2 we've allocated him, and Luka Doncic took 0 more than the 2 that we've already allocated him. Note that this allocation was already counted in the 286 we came up with before, so we need to subtract it and all others where Kobe takes 9 or more shots from our subtotal of 286. How many such combinations are there? Well, that's easy. 3 bricks, 3 basketballs, 6 objects. If we're picking where to put the 3 bricks, that means there's 6 choices for where to put the first one, 5 to put the second one, and 4 to put the third one. And again, we can rearrange the bricks in 3 times 2 times 1 or 6 different ways. A little simplification, and we see that there's 20 different ways in which everyone takes at least 2 shots, but Kobe takes 9 or more shots. And then finally, all we have to do is realize that instead of giving Kobe 9 shots and all the other players 2 shots at the very start, we could have given Ray Allen 9 shots and all the remaining players 2 shots, or Steph Curry 9 shots, or Luka Doncic 9 shots. And each of those scenarios will look just like the scenario where we just considered, where we only have 3 basketballs and 3 bricks left to allocate. What I'm saying is we have 4 choices for which player will be the ball hog, and then regardless of which choice we choose, there'll be 20 different ways to allocate the remaining shots. So it's not just 20 that we need to subtract from our total of 286, it's 4 times 20, or 80, that we need to subtract from the 286. That difference is 206, which is the answer to our question. An important comment I want to leave you with. With just 18 total shots to take, there aren't enough shots to have each player take at least 2, and then have 2 different players take more than 8 at the same time. And that's good because otherwise we would have had to worry about double counting in those 4 different groups of 20 that we subtracted. To show you how problematic that would have been, I want to leave you with this challenge question. As always, feel free to leave thoughts, solutions, methods, and questions in the comments.